And so my name is Bill Buchanan, and I have a true cryptography expert with me today, Martin Albrecht. Hi, Martin.
Hi, Bill. Thanks for having me.
Martin is a professor of cryptography at King's College London and a principal research scientist at Sandbox AQ. He works broadly across the fields of cryptography. His work focuses on the analysis of deployment of, or soon to be deployed, cryptography solutions, and he has responsibly disclosed several vulnerabilities to various public and private stakeholders, such as OpenSSH, Amazon EC2, Apple, Telegram, Jitsi, and Matrix. He further works on designing advanced cryptography solutions and is well known for analysing the security of lattice-based cryptography against classical and quantum computers. So, what's your current role and what does a typical day involve for you?
I split my time between being an academic at King's College London and being a principal research scientist at Sandbox AQ. And in both of these roles, my focus is on research. So I kind of, work on various kind of open questions and try to resolve them. And a day to day is like often quite typical for an academic. You have meetings. There's a lot of admin to do. And then at Sandbox, I split my time between kind of doing that research and also, like being an internal expert and helping out and advising kind of the rest of the team on, cryptographic questions.
So why split your time between industry and academia? Why not stay in academia or in industry? Why do you cross over between the two?
I mean, in some sense, this just like, it was happened by chance. So I was talking to Carlos, who I now kind of work with at Sandbox, and he was talking about kind of what they were doing, and that sounded interesting. So like in some sense, it just happened by chance. I think the kind of why I'm not jumping, doing one or the other. I think so. Deep down, like I really am an academic. I strongly cherish the academic freedom that this role kind of entails. I really appreciate kind of that I get to pick my own research topics, that I can pursue my own agenda, and that I can do this without kind of like having commercial constraints or anything like that. One of the reasons why kind of, the natural question then is, why am I not just an academic then? And the answer is that UK higher education seems to be going from one crisis to the next. And it feels being an academic in the UK is quite a precarious proposition, and academic freedom is curtailed, right? So increasingly management is talking about kind of like unfunded research, and they only want us to work on research for which we have grants. So in some sense, replicating a model as an industry where somebody else decides what problems you work on. And then there's broader issues about academic freedom. So given that this is all a bit precarious, I figured like, maybe try my hand also at an industry role. So far, I'm enjoying it.
Yeah, it's good. And where were you born? Where did you grow up in the world?
So I'm from the eastern part of Germany originally, so in a town called Erfurt, and then I did my undergraduate degree in Western Germany in Bremen.
Yeah, excellent. And so what sparked your interest in maths and cryptography?
So I think that's realistically my mom. So she studied mathematics and then later on worked as a computer scientist in Eastern Germany, and thus, like realistically, really inspired an interest in computer science in me. And then really cryptography, kind of my interest in cryptography in earnest was sparked when I arrived in Bremen at university. So the tradition in Bremen was that every professor would do like an introductory lecture to kind of the new undergraduate students. And one of the professors explained RSA to us.
Excellent.
And that sounded really fascinating. And the reason I had heard of RSA because I was kind of using PGP a lot at the time because kind of in high school I was an activist, and that required us to kind of like be careful about data leakage and so on. So we relied on encryption. And then this professor offered to me to explain, like how does this encryption actually work? And then I was hooked, and the rest is history.
Yeah. And what year would have that been when you
I
first started
started
doing
my
cryptography?
undergraduate in 2001.
Mhm. yeah, yeah. And then what was your advancement after that? Did you do your undergraduate degree and your PhD in the area?
Yeah, so I did my undergraduate degree at it. Like I did a lot of algebra on the side and like took all the cryptography modules that were available. And I did my master's thesis on algebraic attacks on block ciphers. So that's really how I got into the area. And then based off this master's project, I applied to Roy Holloway, where at the time Carlos Sid and Sean Murphy were working, and they were kind of quite well known for algebraic attacks on block ciphers. And so I ended up doing a PhD with Carlos from 2007 to 2010. Afterwards, I moved to the postdoc in Paris with Ludovic Perret and Jean-Charles Fougère. Again, working on algebraic techniques, but there we kind of worked on algebraic techniques on a relatively new problem at the time called learning with errors.
Yeah.
And my job in a project that we were doing on solving learning with errors with algebraic techniques was to write the related work section. So what are all the other attacks? And a fun fact about this work is that we never actually managed to publish this. So it has a fair number of citations, this algebraic attacks on LWE paper, but we never managed to actually formally publish it. And in some sense, I'm still writing the related work section, right? Because from that came an interest in lattice reduction and the BKW algorithm, combinatorial algorithm, and so on. Yeah, so afterwards I went to DTU to work with Gregor Leander, which is also where I met Christian Rechberger, who was there at the time. So that led to the LowMC and MIMC work. And then I went back to Roy Holloway to work with Kenny Patterson on multilinear maps from lattices, and then became a lecturer at Roy Holloway until I moved to King's at the beginning of 2023.
Yeah, yeah. I was an external examiner at Royal Holloway for a few years, and I remember Fred Piper was there at the time. Obviously, dearly departed now, but there was always a great buzz when Fred was around.
Mm-hmm. Yeah.
So, what's your favorite area of cryptography?
To me, cryptography is my favorite area because I don't have to pick. What I really like about cryptography is how broad it is. And I can, often I split my day between, reverse engineering some piece of software or doing some number theory. And all of that fits in. And we kind of broaden this kind of even further. We're now kind of like considering the social foundations, right? Taking into account the cryptography models social relations. And so kind of how do you do that correctly? So I really like that you can do mathematics, you can do computer science, you can do practical work, you can do theoretical work, you can do social science, you can do all of that in cryptography. So like in some sense that there isn't a favorite area is why I like cryptography.
Yeah, I agree. I agree completely. It's like defining a favorite child. You shouldn't really do it because it's all the one topic, as you say. So what topics do you currently teach at King's?
So I currently teach a module called Advanced Topics in Cybersecurity, but given that I'm teaching it, is really advanced topics in cryptography. And so it is in some sense like the idea of the module is to really talk about the particularity of cryptography within the field of cybersecurity. And that is, cryptography is very pedantic about its definitions, right? We have clear definitions and then we have proofs. And we really try to apply a lot of rigor. So we don't do attack and repair cycles, so we try to avoid them. And so I start with that. And then in some sense, for the rest of the module, I dismantle that illusion, right? I talk to students about computational assumptions. We talk about the random oracle model. We talk about the limits of models. We talk about the limits of proofs. So the idea is that students walk away with an appreciation of what cryptography is trying to do and where cryptography still fails to achieve this goal.
Yeah, that's good. So in a research context, which problems are you currently working on?
So there's two broad areas that I'm currently working on. So one is what you could broadly define as funny lattice assumptions. So in recent years, there's been like some sort of consensus, if you like, emerging that the standard assumptions that we have for lattices, the learning with errors problem, the short integer solution problem, and the structured variants, they might not be quite expressive enough to kind of realize all the functionalities that we want. And so people have started introducing variants of these assumptions that enable new functionalities more efficiently. Like think of things like blind signatures or aggregate signatures. And so we need to study these assumptions, right? We don't want to have a proliferation of these unstudied assumptions. And so like a big focus of my work at the moment is to do that. In particular, currently, we are studying a very strange problem. And the problem is I give you a lattice with a short basis. So that would be known as an I-tie trapdoor. And then we say that the inhomogeneous cis problem is still hard. So you still can't find preimages of arbitrary targets if the norm of these preimages is sufficiently close to your trapdoor. So a provocative way of saying this, even if I give you a trapdoor, you can't sample preimages because we have very tight norm bounds. And this problem, we are in the process of showing that this is hard if there is no algorithm that solves hard lattice problems in single exponential time and polynomial memory, which is a somewhat reasonable conjecture that has been made in prior work. And so the reason why we're looking into that is because it allows us to connect some of these newfangled assumptions to all the conjectures from the literature that are also more well supported by cryptanalysis. So that's the one area that I'm focusing on. And the other area is what I previously mentioned, this social foundations of cryptography project. And so the idea is that, as I mentioned, cryptography really prides itself, and I think rightly so, in how rigorous it is, in how much it cares about getting definitions right, and then proving things kind of based on these definitions. But there's a bit of a disconnect in that our games or our ideal functionalities, which are the starting point of our cryptographic solutions, they are somewhat unmotivated, right? In some sense, they come from the intuition of the researchers who kind of propose them. And for many of them, that makes sense, right? A one-way function or pseudorandom permutation, these are objects that feels like they're correct. But when you get to what are actually the security requirements of a digital signature, then things get a lot more complicated. Or what are the security requirements of a messaging system? What security should you aim for under various compromises? And so what we're doing is we're saying we shouldn't leave this to intuition, right? We should leave up to the ethos of cryptography of doing this rigorously. And so we're working, so we are a team of cryptographers and ethnographers. Ethnography is a social science that is, is in some sense our equivalent is that they're very pedantic and very precise and very narrow in their focus. And so together we're trying to establish what are security requirements in some specific settings.
Yeah, it's a big problem to solve. What's the hardness problem that's involved with learning with errors?
So cryptography, unfortunately, like as I previously mentioned, like I talked to my students about computational hardness assumptions, right? We don't know how to realize security guarantees or many security guarantees unconditionally. That is from information theory. But we have to assume that certain tasks are hard, that you cannot compute a certain computation within a certain amount of resources or given a certain amount of resources. And that's what we mean by computational hardness. And so a natural question is, I write down the learning with errors problem. I write down an instance, right? It has a dimension, it has a modulus, it has size of the noise. And the question is like, well, how long do we expect any algorithm to take? How many resources does this algorithm require? And so studying this became really important around the standardization of post-quantum cryptography, because it's one thing to say like, well, there are parameters that will take too long. So the time of the attacker scales much worse than the time of the defender, so to speak, right? So I make my scheme a little bit bigger. The task of the attacker becomes a lot harder. That is fine, but then at some point you need to say like, well, how big do I need to make it in order to resist all attacks that I consider realistic? And so that is really kind of what is at stake in the question of like, what's the hardness of the learning with errors problem?
Yeah, yeah. And so how does a lattice trapdoor actually work?
So the somewhat, depending on how you look at it, you might find this baffling or not, but you can sample, so say A is a random matrix mod Q and it's white, right? So like I pick a matrix and it's white. And it is possible to sample such a random matrix together with a short matrix, so where all the entries are small, that when you multiply them, you get 0 mod Q. And so the short matrix is known as a trapdoor because what it allows you to do using something like Babay's nearest planes algorithm or more sophisticated variants thereof to sample pre-images of arbitrary images, right? So I give you an image, I give you A, and then with my trapdoor, I can compute some vector U. When you multiply it with A, it lands on the image. And you can use that, for example, to sign messages, right? The image becomes essentially your message, and then you say like, well, I can sign this message because I have a short pre-image of A. And the trapdoor then is like sampling such pairs like a matrix A together with a trapdoor, and then also to define sampling algorithms so that this short pre-image doesn't leak anything about the trapdoor, so that an attacker cannot use that to eventually also learn the trapdoor and then forge messages.
Yeah. And so obviously NIST has now defined the migration path away from elliptic curve methods and RSA towards possibly lattice mainly. Mm-hmm. But there are still some questions around this lattice approach through learning with errors. So what do you think the major attacks are against learning with errors?
I mean, in some sense, the kind of two classes of attack that we kind of rely on to cost, right, to give an estimate, like how long would it take an attacker, is the so-called primal and the dual attack. And in some sense, the primal attack is like a straightforward kind of attack. So we have essentially, you can think of the learning with errors problem as defining a random lattice problem. It's like formally called a bounded distance decoding problem for random lattices. And you just solve this problem directly, typically using something called Cannon's embedding for doing unique SVP. But think of this as really, I need to find a short solution. I know algorithms that find short solutions. How long do these algorithms take? That's roughly the primal attack. The dual attack is, the dual. And what you're doing is you essentially use the problem that I've just described when it came to lattice trapdoors. Like without a trapdoor and given a white matrix A, it should be hard to find a short preimage of an arbitrary target. In particular, it should be hard to find a short preimage of 0, right? So because that would give you such a trapdoor, and such a trapdoor would allow you to find short preimages. But if you can find short preimages of 0, then you can use that to decide if a sample that you've been given is an LWE sample or not. So you essentially do an indirect way, and you run a distinguishing attack on learning with errors problem, and then there are tricks to turn that into a key recovery attack as well. And both of these rely on lattice reduction. There's other classes of algorithms, but for concrete parameters, it's almost always true that all you need to consider are these lattice attacks. So that is the state of the art of our understanding of like how fast can you solve these problems.
Yeah. And so do you think the methods that NIST have standardized, Falcon, Dilithium, Kyber, do you think they're going to be fairly robust for the next decade or so?
I mean, like so far it seems this is fairly robust, right? So at the moment, kind of we are arguing about like what is the exact complexity of solving this, and the big problem here is to kind of really have models that are sufficiently fine-grained to consider memory access. But like as it stands, there is nothing to suggest that these would be particularly kind of shaky. But as always in cryptography, we make computational assumptions, right? And so these computational assumptions kind of like have been studied, but we shall see what happens.
Yeah. Obviously, there are difficult areas such as side channel analysis. I assume that the people who are writing the code just now for ML, Chem, ML, DSA are overcoming these problems. But do you think it is possible not for these methods to be robust against side channel analysis?
Yeah, so I think this is like an ongoing area of research, and I'm not too deep in the particularities of various side channel attacks, but it seems doable, right? So it was, of course, also a consideration, kind of like, a point of discussion during the standardization process. And there's like, so go back to, for example, this problem that I mentioned earlier. Like, even if I give you a trapdoor, you can't find short preimages if the norm of these preimages is sufficiently close to the trapdoor. And you can actually use that to argue that a key concern in Falcon side channel attacks isn't probably not a realistic concern. And that is, you might know of Bleichenbacher's attack on ECDSA. So if there is some bias in the nonce value for DSA, then you can use that to do key recovery. And in a similar way, you might think like, well, if I sign the same message twice because I picked the wrong salt, so Falcon prevents us using something called a salt. But say something goes wrong there, then maybe I get short pre-images of 0. These are trapdoor, and that might lead to forgeries. And in some sense, our works is like, it's very unlikely this will lead to forgeries because you would have to overcome this kind of like old cryptanalytic problem of doing lattice reduction in polynomial memory in single exponential time. So like we are learning more about this and understanding where are the actual concerns for side channel attacks and where kind of are we fine.
Yeah. And obviously in areas of blockchain, we use a lot ECDSA and EDDSA just now. I think with dilithium ML DSA, we can't recover the public key, but Falcon allows us to be able to recover it. So there may be applications there. In terms of blockchain, what do you think the migration is likely to be from ECDSA towards these post-quantum methods? I know that nobody has the solution just now, but where would you bet on in it ending up?
I really struggle to kind of like make a bet there. I think there's so many operational concerns that I wouldn't kind of like, fully comprehend in blockchain that I don't feel qualified to kind of like have a bet.
Yeah, it's a difficult one. So what's scaling lattice sieves across multiple devices?
So as I mentioned, it's we assume that it's like we don't know an algorithm that solves hard lattice problems in single exponential time in polynomial memory. But what we do know is algorithms that solve hard lattice problems in single exponential time but exponential memory. So these are called lattice sieves, and these are the algorithms that we use to assess, to pick parameters for these NIST candidates and so on. And so, but these algorithms require exponential memory. And so what you want to do is, well, you at some point run out of RAM in your machine, right? So what you want to do is you want to distribute it across kind of several servers, right? So kind of to use, the RAM available. But then the natural question is like, does it scale, right? Can you actually do this? And this is important because clearly bandwidth between these machines will be somewhat limited. So can you take these lattice sieve algorithms and can you actually parallelize them across multiple servers? And so we've been doing some work, in particular Joe Rowell, who was a PhD student of mine, did a lot of work on this, where we showed not just asymptotically, which was kind of expected, yes, asymptotically you're fine, but also concretely we gave an implementation of such a lattice sieve where we scaled it across like a small number of servers and showed near linear scaling.
Yeah, that's excellent. And so what are cold boot attacks on ring and module learning with error keys?
Yeah, so let's do this in two parts. So the first thing was a cold boot attack. And a cold boot attack is a really like sci-fi sounding kind of attack. And so the idea behind a cold boot attack is that when your RAM loses power, so when you switch off, when you cut the power to, say, your PC, then it doesn't immediately lose the information that is stored there, but this information degrades slowly. And you can slow down this degradation by cooling it down. So the cooler the RAM chip is, the slower it will lose its information. So what you can do is you take off, you could disconnect the power, you cool down the RAM, you take the RAM chip, you put it into a new computer, and when that computer boots up, the first thing it does, it dumps the content of RAM to a hard disk, right? And then what you get is a noisy image of RAM. But this RAM contained the keys, right? It contained your cryptographic keys because they need to be stored somewhere. They are stored in RAM, of course. And so now what you get is noisy copies of the secret key. And then the question is like, well, how hard is it to do error correction on these keys? And what we did in this work on cold boot attacks, we showed that the particular way in which these keys are often stored in ring LWE or in module LWE problems, you can actually recover these keys like from noisy versions of them by using some properties of the NTT, which is kind of used to speed up the computations of these schemes.
Yeah, yeah, it's really interesting. I've seen that attack on other public key methods and where they can freeze
Yeah.
the chips and obviously it can keep some of the memory. So it's really interesting that you can recover the keys from a partial image of the keys. That's a really worrying attack overall. And obviously we've developed all these primitives for elliptic curve methods that we need to scale into a lattice world, and we probably have about 10 years to do that. Some of them are coming naturally, like Shamir shares and so on. But one of the special areas is obviously with zero knowledge proofs and with SNARKs. So can you outline what a lattice-based SNARK would look like?
Yeah, so a SNARK is a succinct non-interactive argument of knowledge. So it's a way of a prover convincing a verifier that a certain statement is true. But instead of just outputting the witness, which kind of like allows the verifier to check it, you output something that's much smaller than the witness. And there's different ways of trying to realize this, and we would like to, in particular, there's pre-quantum, very efficient pre-quantum solutions based on elliptic curves, as you just mentioned. And so we're trying to look for post-quantum alternatives. So the lattice-based SNARK is then to base such a construction on hard problems and lattices, which are presumed post-quantum secure. So then we would get post-quantum secure SNARKs.
Yeah. So how far away are we from getting a lattice SNARK? And would it be too computationally intensive?
I think the problem is like asymptotically things are looking very nice, but then when you
Mm.
concretely you really hit a barrier, right? You're at usually at least 20 kilobytes, if not 50 kilobytes. And I think that seems to be kind of really at the moment, like making things much smaller than this, kind of seems to be a barrier. People who kind of spend more time working on this kind of thing that kind of, yes, several factors, constant factors improvement kind of like are possible. I'm not really in a position to judge that, but like time will tell.
Yeah, excellent. So what's plain text recovery attacks with SSH? I know that you worked in this area and you managed to recover plain text, which is quite worrying because SSH is obviously such a fundamental building block for accessing your cloud system and so on. So what attacks were you able to implement on SSH?
Yeah, like I should first stress that this was 2009 or
Yeah.
2008 and 2009, right? So like these problems have been resolved kind of like for a long time. And essentially what happened is that SSH used a bespoke encryption scheme where they wanted to hide the length of messages sent on the wire, which meant they wanted to encrypt the length field of the messages. But then also you want authenticated encryption, so you want to have a MAC on your ciphertext. But like in order to check the MAC, you need to know how long the message is, right? So you need to know what you need to throw into your MAC in order to check whether the MAC is correct, or even to identify where the MAC begins. So what the scheme would then do is it would decrypt the length field and then wait for the number of bytes as given in the length field, and then it would check the MAC. But now, using some CVC trickery, I can, of course, put my target ciphertext block there. And then, depending on how many bytes I need to send until the server tears down the connection, because the MAC check will definitely fail, or with overwhelming probability will fail, that tells me some information about this plaintext block. That was the rough idea of this attack, and then there's some complications because some other length field checks going on in various implementations. But that was the kind of like the problem that we identified, and then kind of like worked with vendors to resolve.
Yeah, that's great. And that disclosure, it must slow down the publication of the paper. What's if you were to give some advice to other researchers about disclosing vulnerabilities, especially 0 days, what's the process that you have to go through?
So, like, somewhat kind of like provocatively, kind of my number one advice is friends don't let friends disclose through third parties. So, the biggest mistake we made in that disclosure process is that we relied on CPNI, which was, in some sense, a predecessor to NCSC for
Yeah.
handling the disclosure process for us. And they did this that worked very well for all the corporate vendors, right? So because they are well equipped to talk to corporate vendors, there were non-disclosure agreements involved, and that is all very standard for like a corporate environment. It really didn't work with OpenSSH, right? And if you have a vulnerability in SSH, your number one priority must be to fix OpenSSH because it's so dominant.
Yeah.
So the OpenSSH developers, they kind of, in some sense, they look and talk like us, right? Like academics. And so the correct thing that we should have done is just reach out to them directly. It would have been a smooth disclosure. They are well equipped to handle security disclosures. It would have been all fine. But there was a lot of miscommunication between, shall we call it that, between CPNI and OpenSSH, so that when we went live, OpenSSH did not have a full understanding of the problem, right? And that is, of course, unacceptable and really bad. And so the problem really was that we kind of like disclosed through third parties, right? We didn't disclose directly. And there's a varying trend in vulnerability disclosure that companies outsource vulnerability disclosure through third parties like HackerOne and so on. So companies that specialize in this sort of thing. And they're really set up for bug bounties, right? They're really set up to kind of that security researchers can get a payday for finding a vulnerability, which is incompatible with us doing this as academics. And they usually then have pretty strict non-disclosure agreements, right? So if you disclose it, then they will vet it, but you're not allowed to disclose it any further, which of course is unacceptable to an academic team. So really my number one advice is do not use services like HackerOne. Always insist on disclosing directly and make sure before you disclose that you have a good understanding of what you think your responsibility is. Because a company will assert that your responsibility is to them. And I would disagree with that notion. Your responsibility is to those who have to rely on the products of this company. And you might serve these people best by just releasing the vulnerability and warning people to not use a product. So it can be a flawed process, but quite often it works quite well. And even if there's initial hiccups in a disclosure, it is often because the receiving party isn't really experienced in receiving vulnerability disclosures. And so then, like a good strategy is to hop on a call with them and talk them through kind of like, what your expectations are and why you have these expectations and why they are the industry norm. So usually you can de-escalate a disclosure going bad, but not always, right? So like there are horror stories out there where disclosures went horribly wrong. I think our SSH one is like an example of that. But like, we made up in the end.
That's great. Yeah, thanks. So one of my favorite papers that you wrote, and I appreciate it was quite a while ago, was on minimal multiplicative complexity, which is MIMC. And I think now it's having a great impact in zero knowledge proofs. The timing using the methods that you define has reduced so much. So can you actually define what minimal multiplicative complexity actually is and how it might relate to zero knowledge proofs?
Yeah, so like essentially the key idea is when you for many decades, what was the target application for a block cipher? It was either a circuit or it was code on a computer, right? So your target platforms were like some ARM or Intel instruction set, or there were kind of like some circuits. And then both of these say like you really kind of want to work with bits, right? You want to do XORs and ANDs, and then maybe if you're targeting, like a chip, then you also, the adders are very efficient, so you're happy to rely on an adder. But like these are really kind of the target platforms. But now you target new platforms, right? For example, you may think of a zero knowledge proof as the platform in which you want to run your block cipher, because for some reason you need to prove that the evaluation of the block cipher. So now that just defines a new kind of computer in some sense, where the native instruction set isn't the one that you're used to. And MIMC is in some sense leveraging that and saying, well, these schemes, they kind of like natively support like large primes as their kind of fundamental unit instead of two. So why don't we define a scheme that natively works kind of for these large prime fields where you can then implement S boxes by essentially cubing? And the trick here is that, of course, if you write this down as a circuit, kind of as a binary circuit, then this would be kind of quite expensive. But the unit of measurement in these schemes is multiplications. Multiplications in whatever the field is that the scheme is defined over. So now you have a very different trade-off. So these multiplications are now far fewer because they do more work in some sense. And so you get away with kind of much smaller mod P circuits. And that greatly improves performance, you tell me.
Yeah, that's great. And I think they're used in smart contracts to really reduce the complexity and work within a finite field. I think things like hashing methods are really difficult to implement as a zero knowledge proof circuit because it kind of scrambles and it's not really in a finite field. Where I think that your method actually constrains things to a finite field. What have you discovered in the use of multi-device group messaging and WhatsApp?
Yeah, so this is a paper that we had at Eurocrypt last year, and what we did is we took WhatsApp and we reverse engineered it and gave a formal description of what it actually does, and then we gave a formal proof of security in a model which is multi-device group messaging. Device-oriented group messaging, sorry, that's the DOGM is the model that we defined to say like what are the security guarantees of WhatsApp. And so broadly, what we found is that indeed the WhatsApp white paper does a good job of summarizing the protocol, like largely kind of the protocol that is implemented agrees with what's written in the white paper. And also largely the security guarantees are the security guarantees you would expect. There are some caveats. So the first caveat is, and that was already known prior to our work, but it's worth repeating, is WhatsApp does not do cryptographic group management. So if you're in a group in WhatsApp, the members of this group are not cryptographically authenticated. For each of them, there are mechanisms to authenticate that they're keys, but like who is allowed to be in this group is fundamentally a decision of the WhatsApp server. So in principle, the WhatsApp server could add a malicious kind of like an eavesdropper to your group, and an honest client will inform you that a new person has joined the chat. But if you're not careful and you do not check on every single one of your devices, if all participants of the group don't check on every single one of their devices that there hasn't been a new addition to the group, then in principle, like an eavesdropper can be injected. And we think we understand that there are kind of quite some operational concerns for WhatsApp, why they're doing that, why they kind of like don't have these cryptographic guarantees. But cryptographically speaking, that is like an unsatisfactory state of affairs. And it's worth noting that Signal does not have this problem, right? So in Signal, group membership is cryptographically authenticated, as in members of the group sign that this is my view of the membership of this group, and then everybody else can check whether they agree with that. So that is one of the big problems. It's a problem that we also found in Matrix, and I think it's a general problem in many deployed end-to-end secure messenger that they don't do this cryptographic group management. And given that intelligence agencies have proposed to add ghost users to chats, this is a problem. The other thing is, and that is maybe more of like an academic issue, in some sense, WhatsApp, like other deployed secure messengers, doesn't really offer meaningful post-compromise security as is defined in the cryptographic literature. But here we are not aware of any deployed end-to-end secure messenger that actually achieves this. And in fact, the recent work has shown that you can't really achieve it if you want some robustness. So you want to protect against some state compromise because, like some devices were somehow mishandled or lost. So if you want to have a usable system, essentially, you can't have the strong notion of post-compromise security. And so there's a broader conversation to be had within the academic community and also with practitioners of like, what is a correct notion of post-compromise security that is achievable and desirable?
Yeah. Are we heading towards Crypto Wars 3 again with this type of thing? I mean, obviously the EU, the UK, Five Eyes want to break these methods. And as you say, there's the ghost protocol that I think that GCHQ used where a ghost person can come in.
Yeah, I think they only proposed this. I'm not sure they have actually implement
Mm.
this. Like in some sense, didn't we already lose Crypto War 3? Because so number one, in the UK, you can be compelled to hand over your encryption keys, right, under the
Mhm.
law.
Yep. Yep.
And secondly, with the Online Safety Act, there is now the provision there that service providers can be required to eavesdrop on your messages. They're not required to do this by default, but they can be instructed to break end-to-end encryption. So I think in the UK, Crypto War 3.0 is already lost. So
Yeah.
we don't have meaningful legal like guarantees that end-to-end is fine. So
Yeah. But it's difficult if the person doesn't actually know where their private key actually is, then it's really difficult to hand over
yeah, so
a
like
key.
there will be concerns, and I'm sure kind of the law and judges kind of like have their ways of handling that, right? So I guess it's not that different from a witness kind of saying, "I forgot," right? And the court doesn't believe them. But yeah, but like I think it's important to know that we are not heading for Crypto War 3. We already lost Crypto War 3, right? And
Mm.
so if anything, the task would be to regain kind of like these kind of like cryptographic protections that are at the moment undermined. And you've
Mm.
seen this, right? So with the UK government compelling Apple to kind of break their end-to-end encryption of their backups, which now seems to be off the table because the US government, so because of international politics, right? That's why it didn't happen. But given that these sort of moves are also happening elsewhere, you mentioned the EU, there's some initiatives in the US themselves. So as this becomes more prevalent, then I wouldn't rely on, geopolitics to kind of like accidentally kind of like protecting cryptography.
Yeah. Okay. And so classic McEliece has been around for a while. It was one of the first quantum robust methods that was actually proposed, but it's still yet to be standardized by NIST. So what's the main issue do you think that NIST have with classic McEliece, and what's its strengths?
So it has a really unusual performance profile because public keys are big, like 1 MB big, right? Ciphertexts are small. And so it is really, so the question is, what is the application where you don't need to send public keys a lot, but you need to send a lot of ciphertext? In such a setting, classic McEliece would be kind of quite good. NIST came to the conclusion this is not a performance profile that is interesting enough for them to standardize. My understanding is different standardization bodies are looking at it to maybe standardize it. There has been some progress in our understanding of the underlying hard problem recently, which I think, like for example, ANSI kind of shied away a little bit more from classic McEliece. But I think over the next few years, we probably get a bit more clarity on kind of what these kind of new insights mean.
Yeah. And so I think there was the NIST competition for key encapsulation methods, and Kyber won it in the end. And I think HQC is also going to be standardized. But you were part of a team that submitted to New Hope to that competition. I can't remember if it was in the second round or the third round, but it didn't get through. What happened with New Hope?
Yeah, I think first, like my involvement in New Hope was like somewhat tangential in the sense. So we had submitted another scheme called Lima, which was very similar to New Hope, that was kicked out of the competition in the first round. And then New Hope people said like, well, given that you submitted something very similar, why don't you join us? Which we did. Essentially, the module LWE, like think of Kyber as the module LWE version of New Hope. And the module LWE version just is better. So because the performance characteristics are better, you have more flexibility in choosing parameters. You if you have to pick between do I want to instantiate a module LWE or a ring LWE, module LWE is a little bit more conservative, not by much, but I guess a little bit more conservative. So overall, kind of it's just like a better scheme.
Yeah. And so FISTO structure have been around since the 1960s, and I think that was the basis of the Lucifer cipher, DES, 3DES, and I still think it's a useful structure, and it hasn't really been cracked. But obviously, AES came along and wiped the floor with it in terms of performance. Do you think there's still a place for that structure in cryptography?
Yeah, I mean, like, if anything, it's the canonical way to turn your PRF into a PRP, which,
Mm.
you sometimes need. I think is, yeah, like, I think these, we will probably find kind of new applications for them. Like, I wouldn't write it off. I mean, I'm not really that active in symmetric crypto these days, but my understanding is, or maybe that has passed already, is that permutation-based cryptography was all the rage, right? That you don't even do SP networks anymore, but you do what Keccak does. You have one big permutation, and then you build your entire cryptographic stack around that. I'm not sure how that project is going, so maybe it's neither Feistel nor SP networks, but it's kind of like one big bespoke permutation.
Yeah. And there's obviously a big debate in cryptography about whether you should patent or whether you should publish, whether something should be in the public domain, free to use. Obviously, NIST has done that for its standardization. It's been a rocky road, that, but sometimes things have been held back. The RSA patent didn't hold things back, but obviously they did well for the company and the inventors. But the SNAR patents really held back the ED DSA signature. So, what's your opinions on patenting in cryptography? Is it a good thing or a bad thing?
I have never applied for a patent,
Mm.
and I hope I never will. I think there's this saying that if you don't want your cryptography to be used, patent it.
Mm.
I think it's really, I don't think it makes much sense to patent cryptography. Cryptography really, like we care about definitions and standards, and so you really want something that's interoperable, can be scrutinized, can have alternative implementations. So like it really is like given how conservative cryptography is and needs to be, it doesn't feel like I struggle to see a useful use case for patents here. But then I'm not a lawyer.
Yeah. I suppose one thing is if you're creating a company like RSA, they created a company, Reverse Shamir and Edelman wanted to create a company, and MIT wanted to license the technology to the company. That's obviously one thing. So maybe for a spin out company, a startup, then patenting gives them some protection in the market.
It would be, I think, I don't know, maybe somebody has already done this. I think it would be kind of a
Mm.
really interesting study here of just looking at kind of crypto patents and if they actually led to, how instrumental were they in the commercial success of some entities?
Yeah.
Because like my understanding is like a lot of cryptography startups, they start with like some cryptographic innovation, but then soon you realize the marketplace, what it demands is something a lot more mundane.
Mm.
And the bread and butter, like the income generation, is often not the cryptographic innovation, but like a
Yeah.
lot of infrastructure around it. So I think it would be, I wonder if this exists. It would be a fascinating thing, just studying of like, so how much of this, like, the RSA business actually depended on this patent and so on.
Yeah. Yeah, because there's obviously the different universities that were involved at the time. There was Stanford for the Hellman patents. They were less aggressive in following it, but MIT obviously
Yeah.
knew there was some commercialization in there. So I suppose it depends on the university culture too, whether it pushes its academics to patent their work before they publish.
And then it also depends on, what does the university think it is for, right?
Yeah.
So is it for to kind of like directly benefit from some innovation, or is it a body that exists in order to give knowledge to the world?
Excellent. I think that would be a great end point for the podcast. But I've got some other questions
Sure.
for you. So, what does the next decade look like in cryptography? Do you think? I mean, obviously, we're moving into this quantum area, and who knows how long it will take to crack elliptic curve and RSA. But we will have to migrate by 2035. So, but what's what's this chaos going to look like in the next decade or so?
Yeah, I think it's definitely going to be chaotic, right? So we have seen a proliferation of like privacy preserving cryptography in the last 10 years, but a lot of these techniques, we don't really know how to do, kind of translate them efficiently to a post-quantum setting. And that's where these kind of funny lattice assumptions come in, right? Because we don't know how to do this from standard assumptions. People started kind of looking into, well, what if we kind of like make these stronger assumptions? Can we then realize this? Somewhat similar to how pairing-based cryptography enabled like a whole wealth of like new constructions, right? And then it assumes more structure than Diffie-Hellman does. So that's one of the big challenges, right? I think the kind of what you described as crypto wars is also gonna be quite important. So the world is heading, like the time when there was a world market kind of protected and looked after by the US seems to be over. So we're looking at great power competition with spheres of influence. We're also where these great powers kind of like really are careful, like they're trying to maintain their control over their spheres of influence against their adversaries, which means there's a lot more control coming. And so over the next years, we're already seeing this, right? The UK government wants to lean on universities more heavily for its war efforts. So, what privacy will remain under such political conditions is really unclear to me, right? And I think a task for cryptographers is to speak up for privacy, kind of like under these conditions, and to think carefully about like what projects they want to kind of subscribe to and support.
Yeah. And so, what do you think the key problems that we need to solve over the next decade or so?
I think like so in terms in narrow, technical cryptographic terms, it's like how do we lift all this exciting privacy preserving cryptography to a post-quantum setting? I think this would be kind of very important questions for the time to come.
Yeah. And so, my last question, thank you so much for answering all my questions. If you could change one thing about your career, what would it have been?
I probably would have spent more time kind of like in a math classroom than I did. So I do quite mathy cryptography a lot of the time, but it shows that I'm a computer scientist, not a mathematician. I think I took many optional mathematics modules that were available to computer scientists, but still, maybe a dual degree in mathematics and computer science would have served me better in hindsight.
I think you undersell yourself. I think you've learned. I mean, I learn all the mathematics out with a class because we tend not to be teaching that type of maths in classrooms, which is really a very unfortunate. Even in schools, we don't really teach that finite fields type maths. So thank you so much for giving up your time. It's been really interesting. I'm sure we could double the amount of time to talk about all the amazing papers that you've done. So keep up the great work and thanks so much. And hopefully we'll catch up sometime soon. Thank you.
Yeah, I hope to see you soon and thanks so much.
Yeah, thank you.